In this lecture, I will introduce Chapter 10 of Fundamentals of Electric Circuits by Alexander and Sadiku. In this chapter, we're really going to do a lot of the same math that we've done in previous chapters. We're going to do some nodal and mesh analysis. We're going to get into superpositioning, source transformation, finding Thevenin and Norton equivalents. And it's all the same math that we've done before. The only difference is now in AC, what we're going to be doing is dealing with phasors and with some complex impedance. So let's dig into this right away. So the basic steps to analyze an AC circuit, there's really just three steps that we've got to get into. We need to transform the circuit into the phasor or frequency domain. So there we have to understand something about the amplitude. Typically we're going to be talking about sinusoidal circuits, so we want to convert them over into a positive cosine and get a phase that is typically a positive angle. And so we're going to typically express our phase in degrees in this class. Then we want to go about solving the problem using our standard circuit analysis techniques. We're going to be talking about nodal analysis. We're going to talk about mesh analysis and superpositioning. Doing exactly those same techniques, we're going to get a complex value. Then we'll transform that back into a phasor, and we'll know that that phasor is representative of an amplitude and a phase shift, and we should know what our omega is throughout. We'll just keep track of what that particular frequency is, and we'll plug that back in to get us back into the time domain after the analysis. So, nodal analysis. Here, we're just applying Kirchhoff's current law, and that certainly works for any circuit in the frequency domain and the time domain. Again, the first step is to convert that into the frequency domain by calculating the impedances of the circuit elements. So now, we're not going to be worrying about those first-order differential equations, second-order differential equations that we did previously when we were talking about RLC circuits and RL circuits. Now we're going to be thinking about them like resistors that have a complex impedance that is frequency dependent. And also, all of our AC sources are going to appear as phasors, and those are going to be used to represent our amplitude and our phase shift. So here, these are the main formulas that you need to remember for chapters 9 and chapters 10. The impedance of a capacitor given by ZC is going to be 1 over J omega C. And keep in mind, those of us who are electrical and computer engineers, we use J instead of I. It's really the same exact thing, square root of -1 that you've learned in math class. But because I is very commonly used for current, we're not going to be using I, we're going to be using J here. Omega, that is your angular frequency, so we've talked about that previously. And then C is just the value of the capacitance. For inductors, very similarly here we have J omega L. This all gets into really just representing I equals C dV dt, V equals L di dt, just now in the frequency domain. And so that is what we're doing with these J omegas, is really just representing that derivative relationship that we had between voltage and current previously mentioned in earlier chapters. So now our sources are going to have amplitude and phase, and at this point we can do regular Kirchhoff's current law analysis. We can look at all the currents coming into a node, all the currents leaving the node, just as we did several chapters ago, just talking about the DC domain and strictly resistive circuits. The only major difference now is that sources are going to be expressed in terms of phasors. So if they don't have any phase offset, if it's 0 degrees, then we're really just talking about the amplitude, and it's almost treated exactly like a DC source. If there is a phase offset, we'll just convert that into a complex pair. We're going to have a real and complex component, just breaking it down into components along the real axis, components along the imaginary axis, and all of our R, L's, and C's we're going to express as impedances following these formulas. Resistors we don't have to do a thing with. Resistors just say the exact same value. So if you have a 200 mega ohm resistor, a 10K resistor, 1 ohm resistor, all of those are just going to be 1 or 10 or whatever it happens to be, the resistance that you have. But the only thing is you're going to have to convert over these capacitances and inductances to the omega value. So they're going to be frequency dependent. This is very important because what that means is at high frequency, this Z of C is going to be very low. It's going to be approaching 0 as a high value of omega comes in here. As a low value of omega comes in for the L, this is going to behave like a short. A low value here, this is going to behave like an open. And so effectively, we were already doing this when we were in DC. We were just plugging in an omega value of 0. And so we've done all this analysis before, treating omega as 0, because that's what we do for DC. We really could have just started with this chapter, but we started out learning about DC. Now we're going to use those same exact techniques. Nodal analysis might look like this. You can, of course, do a supernode just as usual. So if we're talking about currents in and out of nodes, and you happen to have a voltage source here, here we have a phasor for it, but we're going to treat it the exact same way. We're just going to pull out this source and look at all the currents going into this giant supernode exactly the same. And so that's going to reduce our number of equations by 1. We're going to get that one equation back just by saying V2 plus this source voltage is going to equal V1. But of course here we're not talking about just DC integer type values. We're going to be talking about V2 as a phasor, V1 as a phasor, and of course this source is going to be a phasor. So we'll just add together those phasors, and that will be our representation for the constraint equation. Mesh analysis, really almost exactly the same. You'll notice here all these capacitors have been converted over into complex values. So we've got negative J4 here, negative J2, and those are going to be in ohms. So now it's a complex value in ohms. That's the impedance there. And here we can do a super mesh just like we would before. So if we're talking about doing Kirchhoff's voltage law all the way around a mesh, if you've got a current source in there and you don't know quite exactly what to do in terms of the voltage there, just make a big super mesh around it, and then we can put this constraint equation in here later on to get the current back in there. So of course you're going to have your super mesh go all the way around there, and then you'll know that I4 minus I3 in this case is going to be 4 amps. So we can also mix and match some of our DC values in here. These are just straight DC sources, but now they are operating with some complex impedance that we have in here. Okay, so we're going to convert to frequency domain, then apply Kirchhoff's voltage law as usual. These could have actually been AC sources. It looks like we have the omega values in there already, but they have no phase offset, so they have no complex values in these ones. So 0 phase offset in this case. Superpositioning is going to be almost exactly the same as what we did before, but this is really important if you have sources that are operating at different frequencies. So if you have a source that is operating, let's say one is at 10 hertz and another is at 100 hertz, what omega value would you use when you're trying to compute the complex impedance of a capacitor and an inductor? It's all frequency dependent. So you can't just do it all at once. You're going to have to look at the impact of one source and then the impact of the other source. And so you're going to have to just cut off all of the sources but one, just like we did before with superpositioning, and then you're going to convert everything to a complex impedance for that source. Then you're going to cut off everything except another one and keep doing that for all of the voltage sources or current sources that you have, and then add everything back together. If you're looking for the voltage across a particular component, current through a particular branch, then you just add all of the resulting portions from each of those, each of the contributions from each of the sources together, and you'll get the final result. Source transformation we can do here, just like we did before. We can convert a voltage source in series with an impedance into a current source in parallel with that same impedance. So it's going to be the same impedance, and we just have this relationship here. My voltage source is going to equal that impedance times the corresponding current. So the corresponding current is going to equal the voltage source divided by the impedance. Of course, these are also going to just be phasors. So if you're going to do the math, you need to do the phasor math on it and make sure you can go back and forth So you can just get into the complex numbers. Some cases it's easier just to leave it in phasor and divide through or multiply. In some cases you may want to convert it into a complex number and then put it back together. Thevenin and Norton equivalency are going to be basically the exact same thing. You can apply it to AC circuits the exact same way that you did in DC. The only difference here is that your values may end up being complex. So you may end up with a complex value that you're going to use here for the current, Norton current. You may end up with a complex impedance here. So that means it's no longer just going to be resistive. You might have some capacitive element to it. Op-amp circuits, so long as we're not clipping, we're not in saturation there, operating within the linear range, really analysis is going to be exactly the same. We can do the same thing, just converting everything into a complex impedance as appropriate. We still have the same ideal op-amp characteristics, no current entering either of the input terminals because we assume we have an infinite input impedance. And then the voltage across the terminals is 0, so you have the same exact V plus and V minus that we've talked about before. And so here we want to ensure that no part of the output waveform will result in clipping. Once you have clipping, some of the math doesn't work out quite as well. So you want to make sure, so long as you're operating in the linear range, that everything will work out just fine. So that's really all there is to Chapter 10. All the analysis is the same as what you already know how to do. It's just keeping track of complex pairs. And this week in lecture, we're going to get into several examples of how to make that happen.